Hello there, and welcome to Space Science Before Sleep, where the universe grows quiet, curiosity moves gently, and science takes its time beneath the stars. Tonight we're going to travel outward through the Milky Way and search for the place where our galaxy finally ends. From Earth, the question sounds as though it should have a tidy answer. A galaxy appears in photographs as a bright island of stars surrounded by black space, so perhaps we only need to fly far enough to reach its outer rim. But the Milky Way does not provide a rim. Its crowded regions become sparse, its bright disk gives way to scattered stars, and its visible matter fades long before its gravitational influence disappears. We would cross several boundaries, each meaningful in a different way, without encountering a wall, a gate, or even a modest sign asking us to drive carefully. The edge of the Milky Way is not one place. It is a sequence of endings all quietly overlapping. You can begin this journey without leaving the room. Beyond the window, every star visible to the unaided eye belongs to the Milky Way. The pale band stretching across a dark sky is not a distant cloud floating outside our galaxy. It is our view through the crowded plane of the galactic disk from a position buried inside it. We cannot step outside and photograph the whole structure directly, so astronomers reconstruct it from stellar distances, motions, chemical compositions, radio signals, infrared light, and the effects of gravity. Imagine trying to map a vast forest while standing among the trees. Nearby trunks block more distant ones, paths disappear behind foliage, and the true shape of the forest must be assembled from many partial views. Our galactic map is far better than a guess, but it remains a map made from within. That matters because an edge that looks clean in an illustration may be irregular, warped, and difficult to define when approached from the inside. Before we drift any farther, I'd love to know where in the world you're listening from tonight and what time it is there. And if these slow journeys through space help you relax, learn something new, or simply feel a little less alone beneath the night sky, I'd be grateful if you liked the video and subscribe to Space Science Before Sleep. It helps this quiet corner reach more curious minds who may need something gentle at the end of the day. If you could visit one frontier of the Milky Way, the warped outer disk, an ancient globular cluster, or a distant dwarf galaxy, which would you choose? There is no practical travel paperwork for any of them, which is fortunate because the section marked "Expected Arrival Date" would be rather difficult to complete. Now let the room grow a little quieter. Settle into the pillow, allow your shoulders to relax, and let the details pass without trying to hold every one of them. There's nothing to memorize and no test waiting at the end. If part of the journey fades into sleep, the galaxy will continue turning perfectly well without our supervision. For now, we can carry a few simple questions with us. Where does the bright disk of stars become too thin to call a disk? Does the last region of star formation mark the true edge? Are the ancient stars above and below the disk still part of the Milky Way? What about the globular clusters and dwarf galaxies travelling around it? How far does the galaxy's invisible gas extend? And if gravity continues farther than starlight, should the edge be defined by what we can see, or by what can still feel the Milky Way's pull? To answer those questions, we first need to separate the Milky Way into several components that are often blended together in pictures. Most of its familiar stars, dust clouds and cold gas, occupy a broad rotating disk. Within that disk are regions of enhanced stellar density that we describe as spiral arms. They are not rigid arms made from permanently assigned stars. Stars and gas move through the pattern, rather as vehicles pass through a region of slow traffic. Near the middle lies the central bulge and the more elongated structure of the galactic bar, but our journey is heading the other way, outward from the Sun toward regions where the disk becomes thinner and less crowded. Beyond the main disk is a much fainter stellar halo, a vast three-dimensional population of old stars, globular clusters, and streams of debris. Beyond and among those stars lies diffuse gas. Extending farther still is the dark matter halo, inferred from the motions of visible objects and the gravity required to guide them. Each of these components offers its own possible answer to the word edge. If we define the galaxy by its brightest concentration of stars, the Milky Way ends relatively close to the visible disk. If we define it by the most distant halo stars, it extends much farther. If we include satellite galaxies that orbit within its gravitational domain, the boundary moves outward again. If we include the surrounding reservoir of warm and hot gas, we obtain another uneven frontier. And if we define the Milky Way through its dark matter halo, the galaxy becomes enormously larger than the luminous spiral we usually picture. None of these definitions is dishonest. They simply answer different questions. A city can end at its official boundary, at its last continuous street at its outermost commuter town, or at the point where its lights finally vanish. The Milky Way is less organized than a city, but the principle is similar. Before we can reach its faintest outer structures, we must first leave the region that feels most familiar, the bright rotating disk where the sun has spent its long life moving among the stars. The bright disk does not end where the spiral pattern becomes difficult to see. It simply grows less crowded, less dusty, and less certain. From our position near the sun, the Milky Way can feel almost overwhelmingly full. Stars surround us in every direction, and along the plane of the galaxy they gather into the pale band that crosses a dark sky. Yet the sun is not close to the true center. It travels within the disk, far from the crowded bulge, moving around the galaxy along with billions of other stars. If we begin travelling outward from here, away from the central regions, the first change would not be sudden darkness. The stars would thin gradually. Bright clouds of gas would become less common. The spiral structure would grow harder to recognize. Behind us, the inner galaxy would occupy more of the sky, while ahead the gaps between luminous regions would widen. We would still be inside the Milky Way, but the galaxy would begin to feel less like a crowded city and more like a long road leaving its outer suburbs. The disk itself is not one uniform sheet of stars. It contains several populations layered together, each with its own age motion and chemical history. Many young stars, along with much of the cold gas and dust needed to form new ones, remain close to a relatively thin central plane. Older stars tend to occupy a thicker region, wandering farther above and below that plane as they orbit the galaxy. These broad components are called the thin disk and the thick disk, although neither has a perfectly sharp boundary. The names are useful, but the Milky Way has not arranged itself into tidy labelled compartments for our convenience. As we move outward, we pass through a mixture of stellar ages and orbits. Some stars travel on nearly circular paths around the centre. Others move on more stretched or tilted trajectories. Their motions preserve clues about the galaxy's past, including disturbances, mergers, and the slow reshaping of the disk over billions of years. The spiral arms add another layer to the picture. From a distance they look like enormous structures made from fixed chains of stars, but that impression is misleading. The stars in an arm do not all remain together for the entire lifetime of the galaxy. Instead, the arms are regions where material becomes temporarily more concentrated. Gas can be compressed there, and that compression encourages the formation of new stars. Massive young stars shine brightly and do not live long, so they help trace the spiral pattern while they're still near the regions where they formed. Older stars continue onward, drifting through the pattern as they orbit. A useful comparison is a slow section of traffic on a circular road. The congestion may remain in roughly the same place, even though individual vehicles enter and leave it. The analogy is not perfect because spiral structure is shaped by gravity-gas dynamics and patterns that may change over time, but it reminds us that an arm is not a permanent collection of the same stars. Farther outward, the spiral arms become more difficult to trace. This does not necessarily mean that they stop at a clean line. It means that the material outlining them becomes sparse and uneven. Gas clouds are less frequent. Massive blue stars become rarer. Dust dims less starlight because less dust is present. The outer sky would contain isolated stellar groups separated by larger stretches of darkness, while the inner Milky Way behind us would glow as a broad, complicated structure. From this direction, the galaxy's center would no longer be hidden among nearby stars in the same way. We would be looking back across much of the disk through layers of gas dust and starlight. The view would be beautiful but not especially cooperative. Astronomers prefer structures that hold, still remain flat and label themselves clearly. The Milky Way offers none of these services. Even the size of the visible disk depends on what we choose to observe. Optical light reveals one pattern. Infrared light can pass through dust and reveal another. Radio observations trace cold atomic hydrogen far beyond many of the bright stars. Different groups of stars can also produce different apparent boundaries. A survey focused on young luminous stars may find a smaller active disk than a survey sensitive to faint old stars. This is why a single quoted diameter for the Milky Way can be useful but incomplete. It usually refers to a particular component measured in a particular way. The galaxy has no obligation to make every part of itself end at the same distance. A map of streetlights, a map of roads, and a map of underground pipes would give a city 3 different outlines. None would be entirely wrong. Each would describe something real while leaving other structures outside its chosen border. As we continue outward, the familiar disk begins to lose its visual authority. There is no moment when every star behind us belongs to the galaxy, and every star ahead does not. Instead, the balance changes slowly. The density of disk stars falls. Circular orbits become less dominant. The cold material associated with frequent star formation becomes increasingly patchy. Yet the Milky Way remains present through objects that no longer fit the simple image of a flat spiral. Some stars lie far above or below the central plane. Others follow paths that carry them through the outer regions and back again. Gas stretches beyond the brightest stellar boundary, and the disk itself, which appears so neat in many illustrations, refuses to remain perfectly flat as it reaches into the darkness. Its outer layers bend, broaden, and ripple under influences that are still being reconstructed. We have not yet left the disk, but ahead the galaxy begins to warp. The Milky Way's outer disk does not remain flat. As we move farther from the Sun and deeper into the galaxy's dim outskirts, the broad stellar plane begins to bend with one side, curving above the central level, and the opposite side dipping below it. Astronomers call this structure the galactic warp. It is easiest to trace in the distribution of neutral hydrogen gas, although stars also reveal parts of the same distorted shape. From our imagined position beyond the brighter spiral arms, the disk would no longer resemble a perfectly level plate. It would look more like a wide, shallow wave stretching around the galaxy, subtle in any small region, but unmistakable when seen across tens of thousands of light-years. The warp does not form a sharp crease. It grows gradually, becoming more pronounced in the outer regions where the galaxy's own disk is thinner and less able to resist disturbance. The Milky Way is rotating, but its edge is not calmly following the neat geometry shown in introductory diagrams. The disk also becomes thicker as it extends outward. This widening is known as flaring. Near the inner galaxy, many stars and much of the cold gas remain concentrated close to the central plane. Farther out, their vertical spread increases so the outer disk occupies a broader region above and below the level defined by the inner parts. Imagine a dinner plate whose rim slowly opens into a wider, softer shape. The comparison helps us picture the geometry, but the Milky Way is not solid, and nothing in the disk is physically attached like ceramic. Its stars travel on individual orbits while gas responds to gravity pressure, magnetic fields, and motion through the surrounding environment. The flare emerges from the collective behavior of enormous numbers of objects, each moving freely, yet together forming a large-scale pattern. A neat model may draw the disk with two clean lines. The real galaxy has chosen something closer to a blurred and gently breathing edge. Why should the outer disk bend and widen at all? One reason is that the Milky Way does not live in isolation. Smaller galaxies move around it, pass through its outer regions, and pull on its stars and gas. The Sagittarius dwarf galaxy has been gradually disrupted by the Milky Way, leaving long stellar streams and repeatedly disturbing the galactic disk. The Large Magellanic Cloud, much more massive than its name might suggest, also exerts a significant gravitational influence as it moves through the Milky Way's extended halo. These interactions can create wave shifts and asymmetries that continue long after the closest passage. A distant satellite does not need to strike the disk directly to reshape it. Gravity works across empty-looking space, applying small pulls over immense periods. The effect is less like a hammer blow, and more like someone gently shaking a table beneath a wide bowl of water. The motion can travel far from where the disturbance began. Satellite galaxies are not the only possible cause. Gas arriving from the Milky Way's surroundings may approach on paths that do not align perfectly with the inner disk. The dark matter halo itself may be tilted uneven, or slowly changing in response to nearby galaxies. Magnetic fields and pressure differences can influence the gas while the stars respond mainly to gravity. Several effects may therefore overlap, producing a warp that is not controlled by one simple mechanism. This is where scientific caution becomes important. Astronomers can measure the distorted distributions of gas and stars, and they can build models showing how different forces might produce them. But deciding exactly how much each influence contributes is more difficult. The Milky Way has experienced billions of years of interactions, and its outer disk preserves those events in a pattern that has been stirred many times. We can read the ripples, though not every hand that made them. The warp and flare also remind us that the word edge depends on perspective. If we looked only along the central plane, the outer disk might seem to continue farther in some directions than in others. If we looked above it, we might find stars that still belong to the disk, even though they sit far from the level where most young stars are born. A circular boundary drawn around the galaxy would hide these differences. The outer Milky Way is lopsided, dynamic, and structured by motion. It contains arcs, overdensities, and waves that may belong to the disk, to the stellar halo, or to material being exchanged between the two. Classifying a distant star can therefore require more than knowing its position. Astronomers examine its velocity, orbit, chemical composition, and relationship to surrounding stars. Location is useful, but motion often tells the deeper story. At the edge of a rotating galaxy, belonging is something an object does as much as somewhere it is. As we continue outward, the warp rises and falls behind us, and the flaring disk spreads into a broader, thinner population. The familiar signs of an active spiral galaxy begin to weaken. Dense molecular clouds become less common. Bright stellar nurseries appear only occasionally. The outer regions still contain gas and stars, but the conditions that allow large numbers of new stars to form are harder to maintain. There is no universal line where star formation is forbidden. Instead, it becomes patchy, isolated, and increasingly dependent on local pockets of gas. Ahead lies another possible edge of the Milky Way, not the place where stars end, but the place where the galaxy largely stops making new ones. The disk is still present. Its future, however, is becoming quieter. A galaxy can remain full of old stars long after it becomes quiet enough that new ones are rarely born. As we travel beyond the warped and flaring outer disk, the Milky Way does not suddenly become lifeless. Stars are still present, gas is still present, and gravity is still shaping both. What changes is the ability of that gas to gather into clouds dense and cold enough to collapse. Star formation is not triggered merely because gas exists. The gas must lose energy, become compressed, and remain together long enough for gravity to overcome pressure, turbulence, and motion. In the brighter inner disk, these conditions occur more frequently. Farther outward, the raw material becomes thinner and more widely scattered. The galaxy has not run out of ingredients, but the kitchen has become very large, very cold, and rather poorly stocked in any one place. Most new stars form inside dense molecular clouds, where gas is shielded from some of the surrounding radiation and can cool enough for gravity to draw it inward. These clouds are not spread evenly across the Milky Way. They are concentrated mainly in the disk, especially where spiral structure collisions between gas flows or other disturbances help compress material. As we move outward, the average density of gas declines, and the pressure needed to maintain large cold clouds becomes harder to find. This does not create a perfect threshold. A sufficiently dense pocket may still form far from the main regions of activity, but such pockets become increasingly uncommon. The change resembles leaving a town at night and watching clusters of lit windows become isolated farmhouses. The light does not stop at a municipal line. It simply becomes rarer until each distant glow feels like an exception. The kinds of stars we see also begin to change. Massive blue stars live brief lives by cosmic standards, so they usually remain close to the regions where they formed. When these luminous stars become scarce, they tell us that recent star formation has weakened. Older, smaller stars are different. They can survive for billions of years and continue orbiting long after the clouds that produced them have dispersed. This means the apparent edge of active star formation lies well inside the farthest reach of the stellar population. A region can contain many ancient stars and still have produced almost none recently. The distinction matters because bright young stars dominate photographs. Their absence can make an outer region appear empty even when a quieter population remains. The galaxy becomes difficult to see before it becomes difficult to inhabit with stars. Gas itself can stretch beyond the bright optical disk. Radio observations reveal neutral hydrogen in regions where visible starlight is faint and star formation is weak. This extended gas may be warped uneven and broken into broad structures rather than arranged in a smooth ring. Yet the presence of neutral hydrogen does not guarantee that stars will form there. Much of it may be too warm, too diffuse, or too weakly compressed. Gravity works patiently, but it cannot collapse every cloud simply because astronomers would find the result convenient. Local conditions matter. Passing disturbances, small changes in pressure or interaction with nearby structures may occasionally create a dense region where new stars can appear. The outer disk may therefore contain isolated young stars or small star-forming sites far beyond the main luminous pattern. They are important precisely because they show that the boundary is porous. From inside the Milky Way, finding this boundary is especially difficult. Dust obscures some directions, distance measurements become less certain for faint objects, and the outer disk is warped rather than neatly aligned with our view. Astronomers use different tracers and each reveals a slightly different outline. Ultraviolet light can highlight young hot stars. Infrared observations can penetrate dust. Radio surveys can map atomic gas. Emission from molecular material can identify colder clouds, while chemical measurements help distinguish stars born in different environments. A map based on one tracer may suggest a sharp decline, while another reveals a sparse continuation. This is not a contradiction. It is a reminder that the phrase edge of star formation describes a change in probability, not a universal prohibition. The Milky Way grows less productive gradually, and not in the same way in every direction. The reasons for this decline are still being refined. The lower density of gas is central, but the outer disk is also influenced by the galaxy's gravitational shape, its history of interactions, the arrival of material from its surroundings, and the disturbances caused by satellite galaxies. Some regions may be compressed while others are stretched or stirred. The chemical composition of the gas can also affect how efficiently it cools, and the local radiation environment can change which molecules survive. No single factor draws the final line. Instead, star formation becomes an increasingly rare agreement among several conditions that usually fail to meet. The farther outward we travel, the more the Milky Way seems to live on memory rather than renewal. Young stars appear only occasionally, while older stars continue along orbits established long ago. Eventually, even the scattered signs of recent birth fall behind us. The disk is now faint, broad, and distorted, and the bright inner galaxy has become a distant structure filling one side of the sky. Yet we have still not reached the end of the Milky Way. Beyond the regions where stars are commonly born lies a population that is older, thinner, and arranged in a very different shape. These stars do not remain close to the galactic plane. They move above it, below it, and around it on long tilted paths carrying the chemical memory of the early Milky Way and of smaller galaxies absorbed over cosmic time. The nursery is fading behind us. Ahead lies the archive. The disk grows faint, but the galaxy continues in a different shape. Beyond the regions where young stars are commonly born, the Milky Way opens into a vast stellar halo, a sparse, roughly rounded population, extending above, below, and far beyond the bright rotating disk. The word halo can make it sound like a glowing ring, but this one would be almost impossible to see as a complete structure. Its stars are separated by immense distances, and from any one location the surrounding darkness would dominate. The inner Milky Way behind us would still appear brilliant, compressed into a luminous disk with a crowded central bulge. Around us, however, there might be only a few distant points of light. We would not feel as though we had entered a new layer marked by a border. The change would be recognized through motion and statistics, fewer stars, wider orbits, and a population no longer confined to the galactic plane. Many halo stars are ancient preserving conditions from the early history of the Milky Way. They often contain smaller proportions of elements heavier than helium than stars born later in the disk. Astronomers refer to this property as metallicity, using the word metals rather broadly for nearly every element heavier than hydrogen and helium. It is a useful scientific term, though it would make an actual metalworker reasonably confused. The earliest generations of stars formed from gas that had not yet been enriched by many previous stellar lives. As stars aged, exploded, or shed their outer layers, they returned newly created elements to space. Later stars formed from that enriched material. A star with relatively low metallicity can therefore carry evidence of an earlier chemical environment. It is not automatically one of the first stars, and age cannot be read from composition alone, but chemistry provides an important part of the story. The orbits of halo stars reveal another difference. Most disk stars travel around the galactic center in broadly the same direction, while remaining relatively close to the central plane. Halo stars follow a more varied collection of paths. Some rise far above the disk before falling through it again. Others move on stretched tilted or even oppositely directed orbits. If the disk is imagined as a turning wheel, the stellar halo resembles a few sparks moving around it from almost every angle. The stars are not stationary decorations surrounding the galaxy. They cross the outer regions, approach the inner Milky Way, and travel outward again over enormous periods. By measuring their positions and velocities, astronomers can begin to reconstruct these paths. Motion helps distinguish a halo star from a distant disk star, whose position alone might otherwise appear similar. At the Milky Way's outskirts, where an object is matters less than the history written into how it moves. That history is not entirely homegrown. Some halo stars probably formed within the young Milky Way, or in early structures that became part of it. Many others appear to have arrived inside smaller galaxies that were gradually captured and disrupted. As a dwarf galaxy falls through the Milky Way's gravitational field, tides can pull its stars away, stretching them across vast orbits. Over time, the original system may lose its recognizable shape, but its stars do not instantly mix into a perfectly smooth background. They can retain related motions and chemical patterns long after the parent galaxy has faded from view. Astronomers search for these families by comparing velocity composition and location. It is a form of galactic archaeology performed without ruins in the ordinary sense. The ruins are moving. Each star continues around the galaxy, while carrying a small record of the system in which it formed. For this reason, the stellar halo is not a smooth sphere. It contains streams, shells, clumps, and overlapping remnants from different episodes of the Milky Way's growth. The inner halo has been mixed by repeated orbits, yet even there large stellar populations can preserve signs of common origins. Farther out, where orbital periods are longer, structures may remain recognizable for greater spans of time. The halo shape also depends on which stars are selected to trace it. One survey may emphasize a particular kind of old giant star, while another follows variable stars whose brightness changes in a predictable way. Each tracer samples the halo differently. The resulting maps can look uneven because the halo truly is uneven, but they are also limited by what telescopes can detect through dust distance and the glare of foreground stars. We're assembling a three-dimensional structure from scattered witnesses, and not every witness is equally easy to find. The distinction between disk and halo is therefore useful without being absolute. Some stars have been heated into wider orbits by gravitational disturbances. Others may have formed from gas brought in during a merger. Populations overlap in space chemistry and motion, making the transition between components gradual. Even the phrase outer halo can refer to different distance ranges depending on the scientific question. What remains clear is that the Milky Way's stellar presence continues well beyond the bright spiral structure. By the time we enter these regions, new stars are rare, familiar constellations have dissolved, and the galaxy behind us has become the main source of light. Yet the darkness is not featureless. Hidden within it are concentrated swarms containing hundreds of thousands of stars packed together, far more densely than the surrounding halo. These are globular clusters, ancient systems whose long journeys can help reveal the mass of a galaxy that's becoming increasingly difficult to see. The stellar halo is mostly defined by emptiness, but globular clusters interrupt that emptiness with extraordinary concentration. After drifting through regions where individual halo stars may be separated by immense distances, we might suddenly encounter a compact sphere containing hundreds of thousands of stars gathered into a space only a small fraction of the distance between the Sun and its nearest stellar neighbours. From far away, a globular cluster would appear as a faint rounded glow. As we approached, that glow would divide into countless points increasingly crowded toward the center, until the stars seemed almost layered upon one another. These clusters are not scattered randomly through the disk like ordinary open clusters. Many travel on wide tilted orbits that carry them high above and below the galactic plane through the inner halo, and sometimes far into the Milky Way's outskirts. They are among the brightest and most useful landmarks in a region where almost everything else is faint. Globular clusters are also remarkably old. Many formed during the early history of the Milky Way before the galaxy had settled into its present structure, and before generations of stars had enriched interstellar gas with heavier elements. Their stars generally formed during a relatively brief early period, which means that a cluster can act like a preserved sample of an ancient stellar population. Most of its stars share a similar age and broad chemical history, although careful observations have revealed that many clusters contain more than one stellar population, and are more complicated than the simple systems once imagined. Even so, they remain valuable cosmic archives. By comparing the brightness, temperature, composition, and evolutionary stages of their stars, astronomers can estimate when the clusters formed and study the conditions of the young Milky Way. They are not unchanged relics sealed away from time. Stars evolve within them. Clusters lose members and gravitational encounters slowly reshape their interiors. Ancient does not mean motionless. Inside a globular cluster, gravity produces a very different environment from the quiet halo surrounding it. Stars near the center can pass relatively close to one another, altering their trajectories through repeated gravitational encounters. Binary star systems may exchange partners. Compact stellar remnants can sink toward denser regions. Some stars gain enough energy to migrate outward, while others may eventually escape the cluster entirely and join the broader halo. Over billions of years, the Milky Way itself also pulls on the cluster. Each passage near the galactic disk or inner regions can strip away a few more stars, leaving faint tails along the cluster's orbit. The cluster survives as a recognizable object, but it is slowly being edited by gravity. Imagine a tightly packed flock crossing a broad, invisible wind. Most members remain together while a thin trail gradually forms behind them. The analogy has limits, of course. Stars are not choosing a direction, and the wind is not air. The pattern is written by motion through a changing gravitational field. Those motions make globular clusters especially useful for measuring the Milky Way. We cannot see most of the galaxy's mass directly, but we can observe how distant clusters respond to its gravity. Their positions, speeds, and orbital directions help astronomers estimate how much mass lies inside their paths. They behave rather like buoys carried by an unseen current, revealing the water through the way they move. A single cluster cannot map the entire gravitational field, just as one buoy cannot describe an ocean. But many clusters combined with halo stars, gas clouds, dwarf galaxies, and stellar streams provide a set of distant test particles. The farther from the bright disk they travel, the more valuable they become for studying the extended mass surrounding the Milky Way. Their orbits tell us that the gravitational galaxy is much larger than the luminous one, yet the calculation remains difficult because we observe only a small part of each orbit during a human lifetime, and the Milky Way itself is being disturbed by nearby satellite galaxies. The origins of the clusters are not all identical. Some likely formed within the early Milky Way as its first major structures assembled. Others may have arrived inside smaller galaxies that were later captured and dismantled. Astronomers investigate these possibilities by comparing cluster orbits, ages, and chemical patterns. A group of clusters following related paths may preserve the signature of a common parent galaxy, even after that galaxy has been spread into the halo. In this way, globular clusters become more than clocks. They are surviving pieces of a long merger history. Their present locations do not necessarily reveal where they began. A cluster now moving through the outer halo may once have belonged to a dwarf galaxy, with its own star's gas and dark matter. As that smaller system was pulled apart, the compact cluster endured while the more loosely held material was stretched into streams. The galaxy lost its shape, but some of its older structures continued travelling together. It can also be difficult to decide whether a remote compact object is truly a globular cluster, the dense nucleus of a disrupted dwarf galaxy, or something occupying the blurred region between these categories. Nature is not required to respect the labels created for telescope catalogues. Some objects are unusually large or luminous for clusters. Others contain spreads in chemical composition that suggest a more complex history. A stripped galactic nucleus may resemble an oversized cluster after the rest of its galaxy has disappeared. These ambiguous systems are scientifically valuable because they show how one class of object can be transformed into another. At the Milky Way's frontier, identity is often historical rather than purely visual. To understand what an object is, astronomers must ask where it came from, how it moves, and what its stars remember. As we leave a globular cluster behind, its dense glow quickly contracts into a single point and then fades into the dark halo. Yet its orbit continues tracing a path through the Milky Way's invisible gravitational structure. Farther ahead, we begin to notice that some stars are not gathered into compact spheres at all. They form narrow arcs extending across enormous distances so faint that they can be recognized only when vast surveys compare the motions and chemistry of many stars at once. These are the stretched remains of systems that did not survive as globular clusters did. Gravity has drawn them into long ribbons around the galaxy. The compact archive is giving way to the scattered page. A stellar stream is a galaxy or star cluster being remembered in motion. At first glance, the outer halo appears to contain only isolated stars scattered across enormous distances. But when astronomers compare the positions, velocities, and chemical compositions of millions of those stars, faint patterns emerge. Some stars form narrow bands that curve across the sky, following related paths around the Milky Way. They may be separated by many light years, yet their motions reveal that they once belonged to the same smaller system. Gravity has pulled that system apart without immediately erasing its history. From our imagined viewpoint in the halo, a stream would not look like a bright river. Its stars would be too widely spaced, and most of the ribbon would remain invisible to the eye. Only a careful map would reveal that these scattered points are travelling together along the remains of an ancient orbit. The process begins when a globular cluster or dwarf galaxy passes through the Milky Way's uneven gravitational field. The side facing the galaxy feels a slightly stronger pull than the side facing away. Across a compact object, that difference may be small, but over repeated orbits, it can gradually remove stars from the system's outer regions. Some stars drift ahead along the orbit while others fall behind. The original object continues moving between them, losing more members during each close passage. Over time, the escaped stars stretch into two long tidal tails. A useful image is a loose thread being drawn from a garment, although the stars are not connected to one another like fibers. Once released, each follows its own path through the Milky Way's gravity. Their similar starting positions and velocities keep them arranged in a ribbon for a while. Eventually, the stream broadens, overlaps itself, and becomes harder to distinguish from the surrounding halo. Streams produced by globular clusters are often especially thin because their parent systems are compact and their stars begin with relatively similar motions. Streams from dwarf galaxies can be broader and more complicated. A dwarf galaxy contains stars spread across a larger volume, and it may once have carried gas star clusters and a substantial dark matter component of its own. As the Milky Way dismantles it, different parts can be stripped at different times. The result may be a network of wraps, clouds, and overlapping arcs rather than one tidy line. Some debris can circle the galaxy several times. Older sections become increasingly mixed, while newer sections may remain close to a surviving remnant. Seen in a simulation, the process can look almost graceful. For the dwarf galaxy, however, it is simply a long redistribution of stars. The system does not vanish. It changes address one star at a time. One of the clearest examples is associated with the Sagittarius dwarf galaxy, which is being disrupted as it moves around the Milky Way. Its stars form extensive structures across the halo, providing evidence that our galaxy is still growing by absorbing smaller companions. This is not an unusual accident in galactic history. Large galaxies are expected to assemble partly through repeated mergers and captures, and the stellar halo preserves many traces of that process. Some structures are prominent enough to be linked with known remnants. Others are fainter, older, or more thoroughly mixed. In those cases, astronomers search for groups of stars that share unusual motions or chemical patterns. Stars born in the same smaller galaxy may carry similar proportions of certain elements, giving them a kind of chemical family resemblance. The resemblance is not a perfect label, but when combined with motion it can help separate one ancient population from another. Stellar streams are more than evidence of past mergers. They are also sensitive probes of the Milky Way's present gravitational field. A thin stream follows a path shaped by all the mass around it, including matter that emits little or no light. If the dark matter halo is stretched, tilted, lopsided, or disturbed by a massive satellite galaxy, a stream may bend or precess in ways that reflect that structure. Small gaps or changes in a stream could also be produced when it encounters a dense object, although identifying the cause of any particular disturbance requires care. A passing globular cluster, a concentration of ordinary matter, or an unseen dark matter, subhalo might each leave a gravitational imprint. The stream behaves like a line drawn through an invisible landscape. By studying where the line curves, thickens, or breaks, astronomers can infer something about the terrain. The drawing is delicate and the landscape itself is moving, which is not especially considerate of either the telescope or the person building the model. Interpreting a stream is therefore rarely simple. We observe only the stars bright enough to detect often from one location inside the disk, and we usually know only a small portion of their complete orbits. Distance uncertainties can blur the structure. Different streams may cross in projection, even though they occupy separate regions of space. The Milky Way's gravitational field has also changed over time, as it gained mass and interacted with satellites, especially the Magellanic Clouds. A model that assumes a perfectly smooth and motionless halo may produce an elegant answer while missing part of the real story. Astronomers compare many possible histories, testing which ones best reproduce the observed positions and velocities. Even then, a parent object may remain unidentified. Some streams are the final recognizable evidence of systems that no longer possess a central remnant at all. As we travel onward, the halo begins to feel less like an empty region, and more like a vast archive written in overlapping paths. Some pages remain tightly bound inside globular clusters, others have been pulled into stellar sentences stretching around the galaxy. Together they show that the Milky Way's outskirts were built through contact capture and gradual disruption. Yet not every small companion has been reduced to a stream. Far beyond the bright disk, Entire dwarf galaxies still survive as faint separate systems, each holding its own stars and often far more unseen mass than visible light would suggest. They orbit within the Milky Way's wider domain, raising a new question about the galactic edge. Can an object be a galaxy of its own and still belong to ours? A dwarf galaxy can be separate from the Milky Way and still belong to its wider gravitational family. Far beyond the bright disk, small collections of stars travel through the halo on enormous paths, each retaining enough structure to be recognized as a galaxy in its own right. Some contain millions of stars. Others are so faint that an observer passing nearby might see little more than a loose gathering of dim points against the darkness. They do not resemble miniature versions of the Milky Way with clear spiral arms and glowing central regions. Many are irregular, diffuse and dominated by old stellar populations. Their light may be spread across such a large area that they are difficult to distinguish from foreground stars within our own disk. Yet their members move together, share related distances, and often display a common chemical history. What appears at first to be a slight thickening in a star map can reveal an entire neighbouring galaxy. These systems are called satellite galaxies because they move within the Milky Way's extended gravitational environment. The name suggests a small object following a simple circular orbit, rather like a moon around a planet, but galactic motion is rarely so tidy. Dwarf satellites can follow elongated paths pass through different regions of the halo and be strongly influenced by other massive objects nearby. Some may have orbited the Milky Way for billions of years. Others may have entered its surroundings more recently. Their trajectories can change as the Milky Way grows and as the Large Magellanic Cloud alters the gravitational field around it. Even deciding whether a very distant dwarf is permanently bound can depend on how much mass astronomers assign to the Milky Way and how its motion is modelled. A satellite galaxy is therefore not simply a passenger moving around a fixed central object. It is part of a changing system in which every major member gently pulls on the others. The faintest known companions are often described as ultra-faint dwarf galaxies. Their names are appropriate, although not particularly imaginative. Some contain only a small population of visible stars distributed across a wide region, making their total luminosity lower than that of a single large star cluster. Yet their internal motions suggest that the stars are held inside a much deeper gravitational well than the visible matter alone could provide. These systems are therefore thought to contain large proportions of dark matter relative to their starlight. A dwarf may look almost empty and still possess enough unseen mass to remain bound. This contrast makes ultra-faint galaxies valuable laboratories for studying dark matter, early star formation, and the smallest structures that were able to produce stars after the young universe began to change. They are small by galactic standards, but the questions attached to them are not. Finding these galaxies is difficult because we are searching from inside the Milky Way. Foreground stars fill every image, and a faint dwarf may not appear as a single glowing object at all. Astronomers often identify one by searching for a subtle excess of stars with similar colours and brightnesses, then measuring whether those stars lie at a common distance and move in a related way. Wide-field sky surveys have revealed many such systems, particularly in regions observed deeply and repeatedly, but the survey coverage is uneven, and the disk of the Milky Way hides parts of the sky behind dust and crowded stellar fields. There may be additional companions that are too faint, too diffuse, or too obscured to have been recognized. This is why the satellite census should not be treated as complete. The galaxy may have more attendants than we currently know, some waiting patiently in regions where our view is least cooperative. Dwarf satellites also preserve different chapters of galactic history. Some stopped forming stars long ago, leaving mostly ancient populations. Others retained gas and continued producing stars for longer periods. Their chemical compositions reveal how efficiently they formed stars, how quickly they lost gas, and whether repeated generations enriched the material from which later stars were born. A small galaxy with weak gravity can lose gas more easily than a massive one. Radiation, supernova explosions, and passage through the Milky Way's surrounding gas may all help remove or heat its remaining material. Close encounters with the Milky Way can stretch the dwarf strip away stars and eventually transform it into a stream. We may therefore be seeing surviving galaxies at different stages of the same long process. One remains a recognizable companion, another is being distorted, a third has already been unstitched into a ribbon of stars. Their dark matter content also makes satellite galaxies useful traces of the Milky Way's larger halo. Each dwarf moves through a gravitational field created by the visible galaxy, the surrounding dark matter, other satellites, and the wider local group. By measuring a dwarf's distance and motion, astronomers can test how much mass must exist along its path. But the method contains several uncertainties. We observe only a brief instant in an orbit that may require billions of years to complete. A galaxy's present speed does not reveal its full history without a model. Tidal disturbance can complicate measurements of its internal motion. The Large Magellanic Cloud can shift the apparent balance of the system. It is rather like trying to reconstruct the paths of many slow-moving boats from one photograph, while the harbour itself drifts sideways. The information is real. The interpretation requires patience. There is also no contradiction in calling a dwarf galaxy both independent and part of the Milky Way system. It formed its own stars, developed its own chemical history, and may possess its own dark matter halo. In that sense, it is a separate galaxy. Yet its present motion may be governed largely by the Milky Way, and its future may involve gradual disruption or merger. Membership in a galactic environment does not erase identity. The same principle appears at larger scales, where the Milky Way belongs to the local group without ceasing to be a galaxy of its own. Boundaries in astronomy often describe relationships rather than ownership. A remote dwarf can therefore stand beyond nearly all of the Milky Way's bright stars and still tell us that we have not left the galaxy's domain. As we continue outward, the faint satellites do not mark one final border. They occupy a broad region, some nearby in galactic terms, others moving through the distant halo where the Milky Way's influence overlaps with the pull of larger companions and neighbouring galaxies. Ahead, two dwarf systems become far more prominent than the rest. From dark skies in Earth's southern hemisphere they can be seen without a telescope, as pale clouds detached from the Milky Way's band. They are not passive ornaments. Their mass motion and surrounding gas are reshaping the outskirts of our galaxy. To understand the edge of the Milky Way, we must follow the Magellanic Clouds and the wake they leave through the dark. The outer halo is not standing still, and the Magellanic Clouds help us see it move. From dark locations in Earth's southern hemisphere, the large and small Magellanic Clouds appear as two pale patches, separated from the bright band of the Milky Way. They can look like fragments that have drifted away from our galaxy, but each is a dwarf galaxy with its own stars, gas internal motions, and long history. The Large Magellanic Cloud is the more massive of the pair, and its influence extends far beyond the stars we can see inside it. As it travels through the Milky Way's outer environment, its gravity pulls on halo stars, disturbs the distribution of dark matter predicted by current models, and even shifts the motion of the Milky Way itself. The smaller galaxy is not simply circling an unmoving giant. Both participants respond. The dance is unequal, certainly, but the dance floor moves. The large and small Magellanic Clouds have also interacted strongly with each other. Their gravity has disturbed their shapes and helped draw out an enormous system of gas stretching across the sky. The best-known part is the Magellanic Stream, a long ribbon composed mainly of hydrogen that trails through the Milky Way's surroundings. Another gaseous structure extends ahead of the cloud's motion, although its origin and relationship to the system remain subjects of continuing study. These features are much easier to map with radio telescopes than with ordinary visible light. To human eyes, most of the stream would be completely dark. Radio observations reveal it because neutral hydrogen emits at a characteristic wavelength, allowing astronomers to trace gas even where very few stars accompany it. The result is a remarkable picture. Two small galaxies moving with an extended wake of material, their history written not in a bright tale of stars, but in faint hydrogen spread across a vast region of sky. The exact origin of all that gas is complicated. Some may have been removed through gravitational interactions between the two clouds. Some may have been stripped or reshaped as the system encountered the Milky Way's extended gaseous halo. Gas moving through a surrounding medium experiences pressure, especially when it belongs to a relatively small galaxy, with limited gravity holding it in place. The process is often compared to air pressing against a cyclist, although the galactic version involves extremely thin plasma enormous distances and timescales, for which the bicycle would require unusually durable tires. Gravity and pressure can work together, and the relative importance of each process may vary along the stream. Astronomers study the gas's velocity composition, temperature and structure to reconstruct where it came from and how it has changed. The answer is unlikely to be one clean event. The Magellanic System has been shaped by repeated encounters internal activity and its passage through a Milky Way environment that is itself uneven. The large Magellanic Cloud also leaves a gravitational wake. Imagine a boat crossing calm water. The hull displaces the water and creates a region of altered motion and density behind it. The large Magellanic Cloud does something loosely similar as it passes through the Milky Way's halo, except the surrounding material includes widely separated stars, and according to the leading cosmological model, a much larger quantity of dark matter. The analogy must be treated carefully, because the halo is not a fluid in the ordinary sense, and its particles do not collide like water molecules. Yet gravity allows a wake-like concentration to develop. Matter is focused and disturbed by the passing galaxy, while the Milky Way's broader halo responds collectively to the pull. Large stellar surveys have mapped an uneven distribution of distant halo stars consistent with this predicted response. The outer Milky Way is therefore not a calm spherical background. It is carrying the imprint of a massive companion moving through it. This disturbance matters because astronomers often use halo star streams, globular clusters and dwarf galaxies to estimate the Milky Way's mass. In a simple model, these tracers orbit inside a smooth gravitational field centered on a stationary galaxy. The large Magellanic Cloud makes that picture less reliable. Its pull changes the paths and velocities of distant objects. It also causes the inner Milky Way, including the disk and its central regions, to move in response. Measurements made relative to that moving inner galaxy can create patterns that would not appear if the Milky Way were perfectly settled. Researchers must therefore model both the direct attraction of the large Magellanic Cloud and the larger wake induced in the halo. Otherwise, some motion attributed to the Milky Way's total mass or dark matter shape might partly reflect the current interaction. The difficulty is scientifically useful. A disturbance is not only a complication, it is also a probe. The strength and structure of the wake may help constrain the mass of the large Magellanic Cloud, the shape of the Milky Way's outer halo, and perhaps the behavior of dark matter on galactic scales. But each conclusion depends on models of the cloud's earlier path. Many orbital reconstructions suggest that the Large Magellanic Cloud may be making an early close passage around the Milky Way, rather than having completed many quiet revolutions, although the detailed history remains sensitive to the assumed masses of both galaxies. A heavier Large Magellanic Cloud loses energy, differently creates a stronger response and alters the Milky Way more substantially. The Small Magellanic Cloud adds further complexity because the two dwarfs have pulled on each other while also responding to our galaxy. Reconstructing their journey is rather like discovering several sets of footprints in moving snow. The tracks are visible, but the ground has changed while every traveller was crossing it. As we move beyond the clouds, their visible stars recede into concentrated patches, but the structures associated with them continue across the halo. Streams of gas reveal contact with an environment that otherwise seems almost absent. Disturbed halo stars reveal the gravitational passage of a companion. Their motions suggest that even the Milky Way's dark matter cannot be treated as a perfectly smooth, motionless shell. The galactic frontier is active, exchanging material and responding to every sufficiently massive visitor. Yet the wake also raises a quieter question. What is the Large Magellanic Cloud moving through? The space surrounding the stellar halo is not a perfect vacuum. It contains a thin extended mixture of warm and hot gas, along with cooler clouds and material arriving from or leaving the galaxy. We have followed the boat and found its wake. Now we must look more closely at the nearly invisible atmosphere through which it travels. The Milky Way has an atmosphere, although no traveller would recognize it as one. Beyond the bright disk and among the sparse stars of the halo lies an enormous region of gas known as the circumgalactic medium. It surrounds the galaxy in a thin, irregular volume extending far beyond most of the visible starlight. This material is not arranged in a smooth shell, and it does not produce a blue sky weather or any especially helpful indication that we've entered it. Its particles are separated by distances that would qualify as an excellent vacuum on Earth. Yet across the scale of an entire galaxy, even such a low density can add up to a substantial amount of matter. The gas can slow material stripped from satellite galaxies absorb particular wavelengths of light cool toward the disk and carry energy outward from regions where stars have formed. The Milky Way's luminous body is therefore surrounded by something closer to a vast, shifting reservoir than empty space. This circumgalactic gas exists in several states at once. Some of it is relatively cool by galactic standards and concentrated into clouds. Some is warm and highly ionized, meaning that energetic radiation or collisions have removed electrons from its atoms. Another portion is heated to temperatures at which it emits primarily in ultraviolet or X-ray wavelengths, rather than visible light. These phases overlap, mix and change as the gas moves. A cool cloud entering a hotter environment may gradually break apart or evaporate. Hot gas may radiate energy, cool, and become denser. Shock waves can raise temperatures, while turbulence can stir together material with different histories. Calling the whole region an atmosphere is useful because it surrounds the galaxy and interacts with objects passing through it, but the analogy quickly reaches its limit. Earth's atmosphere is held close to a solid planet and becomes rapidly denser near the ground. The Milky Way's outer gas is spread across hundreds of thousands of light years, shaped by gravity, radiation, magnetic fields, and the accumulated activity of billions of stars. Much of this gas would remain invisible if astronomers had to rely on its own glow. Instead, they often detect it by placing a brighter object behind it. A distant quasar can provide a strong beam of light that travels through the Milky Way's surroundings before reaching a telescope. Atoms and ions in the intervening gas absorb very specific wavelengths, leaving narrow dark features in the quasar's spectrum. These absorption lines reveal which elements are present, how strongly they are ionized, and how the gas is moving along our line of sight. Ultraviolet observations are especially valuable for tracing warm ionized material, while X-ray instruments can investigate hotter components. Radio telescopes map cooler neutral hydrogen clouds. Each method reveals a different layer of the same extended environment. It is rather like learning about a nearly invisible fog by shining lamps through it from many directions, except the lamps are distant galactic nuclei and scheduling them is considerably less convenient. The gas surrounding the Milky Way is not merely leftover material waiting outside the disk. It participates in a continuing cycle. Stars form from cold gas and massive stars later return energy, and enriched material through winds and supernova explosions. Some of that matter remains near the disk while some is driven upward into the halo. Galactic fountains can carry gas away from star-forming regions before gravity draws part of it back. More energetic outflows may travel farther, mixing with the circumgalactic medium and spreading elements manufactured inside stars. At the same time, gas from the Milky Way's wider surroundings may fall inward cool and eventually contribute to future star formation. The process is neither a steady inward rain nor a simple outward wind. Material rises, falls, stalls, fragments, and mixes. A galaxy feeds itself partly by recycling what it has already used, and partly by receiving new material from beyond its brighter regions. The outskirts are not a storage cupboard, they are a slow circulation system. Satellite galaxies encounter this environment as they move through the halo. Their own gas can experience pressure from the surrounding medium, especially when the satellite's gravity is too weak to hold that gas securely. Over time, material may be stripped away and added to the Milky Way's outer reservoir. The Magellanic Stream is one dramatic example of gas distributed through this region, although its detailed origin reflects both gravitational interactions and contact with the Milky Way's gaseous surroundings. Smaller clouds may be falling toward the disk moving away from it, or following paths whose histories are difficult to reconstruct. Measuring their velocities tells astronomers how they move relative to us, but not always their complete three-dimensional journeys. Distance is especially challenging. A cloud projected against the halo may be much nearer or farther than it appears. The gas has no bright surface on which to place a useful label. Astronomers must infer its location from indirect clues, which is a recurring habit at the galactic frontier. The total amount of matter contained in the circumgalactic medium remains uncertain. Cosmological models suggest that galaxies should be associated with more ordinary matter than we can easily count in their stars and cold disk gas. Some of that missing material is expected to reside in extended warm and hot halos, but determining how much requires knowing the gas density, temperature, composition, and three-dimensional distribution. Absorption measurements usually sample narrow paths rather than the whole volume. Emission becomes difficult to detect when the gas is extremely diffuse. Clumps, filaments, and temperature variations can change the inferred mass. Even the outer boundary is unclear because the Milky Way's gas gradually blends with material belonging to the local group and the wider intergalactic environment. A model may assign a useful radius, but nature does not provide a membrane at that location. The atmosphere simply becomes harder to distinguish from everything around it. As we continue outward, the gaseous halo grows thinner and more ambiguous. Cooler clouds become isolated. Hot plasma merges into a broader background. Behind us, the Milky Way's disk is now a distant luminous structure wrapped in layers that human eyes could never see directly. Yet objects moving through this region still curve, accelerate, and remain bound as though a much larger galaxy surrounds them. Gas alone cannot account for that gravitational reach. Neither can the scattered halo stars, globular clusters or dwarf satellites. The visible components are fading, but the motions continue to insist that more mass is present. To find the next edge of the Milky Way, we must stop asking what shines and begin asking what moves. At the Milky Way's outer frontier, motion becomes more informative than light. The stars around us are now sparse. The glowing disk is far behind, and much of the surrounding gas is too thin to see directly. Yet the few objects moving through this darkness do not travel at random. Halo stars sweep along elongated paths. Globular clusters rise above the disk and return. Dwarf galaxies curve through the wider gravitational environment, while stellar streams stretch around the Milky Way like faint lines drawn across an invisible landscape. Each path is being shaped by gravity. By measuring those paths, astronomers can estimate how much mass the galaxy contains and how far its influence extends. We may not be able to photograph the Milky Way's full gravitational structure, but we can watch what it does. The outer galaxy reveals itself through the quiet bending of motion. The basic principle is familiar. If an object travels around something, its motion depends on the gravitational pull acting upon it. A planet's orbit reveals the mass of the star it circles. A moon's path helps reveal the mass of its planet. In a galaxy, the situation is far more complicated because the mass is not concentrated in one central point. Stars' gas, stellar remnants, and dark matter are distributed through a vast three-dimensional region. Even so, the speed and direction of an orbiting object contain information about the total mass influencing it. If a distant halo star is moving rapidly yet remains bound to the Milky Way, the galaxy must possess enough gravity to keep that star from escaping. If a satellite galaxy follows a curved path through the halo, something must be supplying the inward pull. Motion becomes a scale for weighing matter that cannot be placed on any ordinary balance. One useful idea is escape velocity, the speed an object would need to travel away from the Milky Way without eventually being drawn back. Escape velocity is not the same everywhere. It is higher in regions where the gravitational field is stronger and generally lower farther from the galaxy's central mass. Astronomers measure the velocities of stars, especially those moving through the halo, and compare them with models of the Milky Way's gravitational potential. A star moving quickly does not automatically escape. Its direction matters, its location matters, and the mass distributed far beyond it can matter as well. Some stars follow long orbits that carry them outward before gravity turns them back. Others may truly be unbound, perhaps accelerated by interactions with compact objects, disrupted stellar systems, or past encounters. Distinguishing between a distant traveller and a permanent departure requires more than one snapshot. The galaxy rarely stamps its stars with return tickets. Measuring three-dimensional motion is itself a demanding task. A star's movement toward or away from us can be estimated from shifts in the wavelengths of its light. Its sideways motion across the sky is called proper motion, and for distant objects that apparent shift can be extremely small. Precise surveys measure stellar positions repeatedly, gradually revealing how stars move against the more distant background. Distance must also be estimated, because the same tiny angular motion can represent very different physical speeds depending on how far away the star is. Once astronomers combine position, distance, radial velocity, and proper motion, they can reconstruct a star's present velocity through space. They can then test possible orbits within different models of the Milky Way. The result is not a film showing the star's complete journey. Human observations cover only a minute fraction of an orbit that may last hundreds of millions or billions of years. We see one frame and use physics to infer the rest. Globular clusters and dwarf galaxies extend this measurement into regions where individual stars become difficult to observe. Because these systems are brighter and contain many stars, their overall motion can sometimes be traced at enormous distances. Their paths help estimate how much mass lies within the outer halo, but they do not all provide identical answers. The number of known distant traces is limited, and their orbits may not be distributed evenly. A small sample can give a misleading picture if several objects arrive together as part of the same captured galaxy. The Large Magellanic Cloud adds another complication by pulling on the Milky Way and altering the motions of outer halo objects. The galaxy cannot always be treated as a perfectly stationary center surrounded by obedient test particles. It is moving, responding, and being disturbed. The mathematics may prefer a quiet, symmetrical Milky Way. The actual Milky Way has other plans. Stellar streams provide a particularly delicate way to map this gravitational field. A thin stream follows an extended orbit, giving astronomers many related stars along a long path rather than one object at a single location. If a model of the Milky Way's mass bends the stream in the wrong direction, or spreads it too quickly, the model may be missing part of the gravitational structure. Yet streams also carry the history of their parent systems, and they can be disturbed by satellite galaxies, star clusters, or concentrations of unseen matter. Their present shape reflects both the steady pull of the Milky Way and the interruptions encountered along the way. Researchers therefore compare detailed simulations with observed positions and velocities, adjusting the distribution of galactic mass until the modelled stream resembles the real one. It is like reconstructing an unseen hill by studying a ribbon laid across its slopes, except the ribbon is moving. The hill may be changing shape, and we're standing somewhere on the hill while attempting the measurement. When all these traces are considered together, one conclusion becomes difficult to avoid. The visible stars and gas do not provide enough gravity to explain the motions observed throughout the Milky Way. Far from the bright disk, objects continue to behave as though they are embedded within a much larger concentration of mass. This unseen component does not end where the starlight fades. It surrounds the luminous galaxy and dominates the gravitational landscape of its outer regions. Astronomers call it the dark matter halo, not because it forms a dark surface, but because it does not emit, absorb, or reflect light in the ordinary ways that make matter easy to observe. We have reached a boundary that can be measured only indirectly. The lamps of the galaxy are disappearing behind us while the shape of an invisible hill continues beneath every orbit. The dark matter halo is the Milky Way's largest component, yet it contributes none of the familiar light by which we usually recognize a galaxy. It does not glow like stars, shine in radio waves like cold hydrogen, or appear as a luminous mist around the disk. Its presence is inferred from gravity, from the speeds of stars, the motions of satellite galaxies, the shapes of stellar streams, and the way the outer Milky Way remains held together long after visible matter has become sparse. If the galaxy contained only the stars and gas, we can detect many of these objects would move differently. Some would travel too quickly to remain bound. The observed motions require a deeper gravitational field extending far beyond the bright spiral disk. The Milky Way we see is therefore nested inside a much larger structure that we do not see. The luminous galaxy is not the whole galaxy. It is the part that turns its lights on. Astronomers describe this unseen structure as a halo because it surrounds the disk in 3 dimensions rather than sharing its thin, flattened shape. The exact geometry is still uncertain. It may be broadly rounded, somewhat stretched, or subtly distorted by the Milky Way's history and by the pull of nearby galaxies. Its density is expected to be greater toward the inner regions and to decline gradually with distance. There is no reason to imagine a hollow shell with a clear inner and outer surface. Dark matter is modelled as being distributed throughout the galaxy, including the region occupied by the disk, while becoming dominant in the outer gravitational budget where visible matter thins away. A useful image is a broad hill beneath a small illuminated town. Near the town centre, buildings and roads attract most of our attention. Farther out the lights disappear, but the slope of the hill continues. Objects still roll according to terrain that remains present even in darkness. The word dark can also be misleading. It does not necessarily mean black material that blocks light. Dark matter appears to interact very weakly, if at all, with ordinary electromagnetic radiation. It does not form glowing clouds, reflect starlight, or produce the absorption patterns used to trace ordinary gas. Its most obvious influence on galactic scales is gravitational. We do not yet know what it is made of. A wide range of particle candidates and alternative explanations have been investigated, but no dark matter particle has been conclusively identified. The halo is therefore both a practical part of modern galactic models and a reminder of incomplete knowledge. Astronomers can map aspects of its gravitational influence without knowing the fundamental identity of the substance producing that influence. It is rather like learning the shape of an invisible object by watching how countless pendulums swing around it. The behavior is measurable. The hidden cause remains under examination. The halo is not expected to be perfectly smooth. In the leading picture of cosmic structure formation, large galaxies grow inside dark matter halos assembled through many mergers. Smaller halos fall inward, and some survive as subhalos orbiting within the larger structure. A portion of these subhalos may contain enough ordinary matter to form visible dwarf galaxies. Others may have lost their gas and stars, or may never have formed many stars at all. They would then remain almost entirely invisible, detectable only through gravitational effects. Researchers search for such effects in the motions of stars in gravitational lensing and in disturbances along narrow stellar streams. A small gap or bend in a stream could indicate a past encounter with a compact concentration of mass, but the interpretation must be cautious. Ordinary star clusters, giant molecular clouds known satellite galaxies, and imperfections in the stream model can produce similar features. An invisible explanation should not be chosen merely because it is more mysterious. Where then does this dark matter halo end? One common answer uses a boundary defined by cosmological models. Astronomers may choose a radius within which the average matter density is a specified amount greater than the cosmic background. Such a definition creates a useful scale for comparing galaxies and estimating their total masses. It is often associated with terms such as the virial radius, although the precise convention can vary. This boundary is not a physical wall. A spacecraft would not cross it and notice a sudden change in darkness temperature or gravity. The density of dark matter would continue decreasing smoothly beyond the chosen line, and material could move across it in either direction. The boundary is more like a contour marked on a weather map, scientifically useful, mathematically defined and absent from the air itself. The universe has once again declined to draw its diagrams in permanent ink. Other definitions may place the meaningful edge elsewhere. One can ask where matter has completed enough orbital motion to become part of the settled halo, where recently infalling material reaches the outermost point of its first orbit, or where the Milky Way's gravitational influence becomes comparable to that of neighbouring systems. Each question produces a different scale. The halo is also not isolated from the Large Magellanic Cloud Andromeda and the wider local group. Their gravitational fields overlap and evolve. The Milky Way's own centre of motion shifts in response to massive companions, while the outer dark matter distribution may develop wakes and asymmetries. A perfectly spherical, unchanging halo is a convenient first model, not necessarily a complete portrait. The farther outward we travel, the harder it becomes to separate the Milky Way's private gravitational territory from the shared landscape around it. From our imagined position near the halo's distant reaches, the bright disk would now look surprisingly small. Nearly every object visible to the unaided eye would lie behind us, concentrated into a narrow luminous form surrounded by faint companions. Around us, dark matter would not appear as fog or shadow. There would be no surface to touch and no boundary to photograph. Its presence would be carried in the paths of distant stars, clusters, and galaxies, moving through the unseen field. This is the deepest edge we have encountered so far, not the end of matter, but the fading of a galaxy's distinct gravitational identity. Beyond this region, the Milky Way does not meet empty space. It approaches the extended influence of Andromeda, the motions of smaller galaxies, and the diffuse matter of the local group. The invisible hill is becoming part of a larger landscape. The Milky Way does not end by meeting empty space. It fades into a region already occupied by other galaxies, diffuse matter, and overlapping gravitational fields. This wider environment is called the local group, a collection of galaxies bound together on scales much larger than the Milky Way's bright disk. Our galaxy and the Andromeda Galaxy are its two dominant members, accompanied by the Triangulum Galaxy and many smaller systems. Some of those smaller galaxies travel close to one large member. Others occupy more distant paths where the question of membership becomes harder to answer. From the far edge of the Milky Way's dark matter halo, Andromeda would no longer be merely a faint patch in Earth's night sky. It would represent another enormous concentration of stars, gas, and dark matter whose gravitational influence extends into the same broad landscape. We have left the familiar spiral arms far behind, but we have not entered a cosmic wilderness. We've entered shared territory. A useful way to picture this region is as a landscape containing several wide hills. The Milky Way occupies one deep gravitational valley, Andromeda another, while smaller galaxies move across the slopes between them. Near the centre of each large system, the local pull is dominant and belonging is relatively easy to describe. A star deep inside the Milky Way's disk is clearly part of our galaxy. A star deep inside Andromeda is clearly part of that one. Farther out, the slopes become shallower and begin to overlap. There is no fence where one influence ends and another begins. Gravity from both galaxies is present everywhere, along with smaller contributions from every other mass in the group. The practical question is which gravitational structure controls an object's motion most strongly, and whether that object remains bound to one galaxy, to a smaller subgroup, or to the local group as a whole. This is why a distant dwarf galaxy can be difficult to classify. Its present position may place it closer to the Milky Way, but its velocity may suggest a more complicated history. It may be approaching for the first time, moving away after an earlier passage, or travelling on an orbit influenced by the combined mass of the local group. Determining whether it is securely bound requires estimates of its three-dimensional motion and of the Milky Way's total mass, both of which contain uncertainty. The Large Magellanic Cloud complicates the picture further because it is massive enough to carry its own smaller companions and to shift the motion of the Milky Way in response. A dwarf galaxy near the clouds may have entered the Milky Way's surroundings as part of that system rather than arriving alone. Galactic membership begins to resemble family history. The present address matters, but so does who arrived with whom. The gas between these systems is equally difficult to assign. The Milky Way's circumgalactic medium becomes thinner with distance, while Andromeda possesses an extended gaseous environment of its own. Between them lies diffuse material associated with the broader local group and the intergalactic medium beyond it. These components may overlap without forming a clean surface. A cloud of gas does not carry a label stating which galaxy owns it. Astronomers examine its position velocity, temperature, chemical composition, and relationship to nearby structures, but even then the answer may remain uncertain. Some material may be falling toward a galaxy. Some may have been expelled from one in the past. Some may have been stripped from a smaller companion and mixed into the shared environment. Matter at the galactic frontier is often in transit. The edge is not merely where one structure ends, it is where exchange becomes more important than possession. The Milky Way and Andromeda are themselves moving toward a future interaction, but that distant event is not needed to understand the present boundary. Even now, their extended gravitational fields belong to one connected system. The motion of smaller galaxies throughout the local group reflects the total distribution of mass, not only the visible stars in either large spiral. Astronomers use these motions to estimate the group's combined gravitational structure, although the limited number of traces and uncertainty in their paths make the calculation difficult. The local group is not a rigid collection orbiting a single central point. It is a changing arrangement whose largest members pull on one another, while smaller galaxies respond to both. Imagine two watersheds approaching across a broad highland. Rain falling near one side eventually joins one river, while rain falling near the other joins another. Near the divide, a very small change in position can lead to a different destination. The gravitational version has no visible ridge, and every part of the landscape is slowly changing. There are useful mathematical ways to define outer limits within this shared environment. Astronomers may identify regions where material is likely to remain bound to one galaxy surfaces, where the average outward expansion of the universe is balanced by local gravitational attraction, or boundaries associated with the orbital histories of infalling matter. These definitions help organize models, but they do not all produce the same line, nor are they permanent. As galaxies move and gain or lose material, their effective domains change. An object near a boundary today may follow a path that carries it into another region later. Even the expansion of the universe, so important on larger scales, is not pulling the local group apart in the ordinary sense. The group's own gravity dominates its internal motion. Yet beyond its wider bound environment, cosmic expansion becomes part of the story again. The edge of the Milky Way is therefore nested inside the edge of a group which is nested inside structures larger still. Looking back now, the galaxy we left has become a luminous disk embedded in a nearly invisible series of larger components. The warped stellar edge disappeared first. The ancient halo stars continued beyond it. Globular clusters and streams carried evidence of the Milky Way's history into the darkness. Satellite galaxies marked a wider gravitational family. Diffuse gas extended farther than most visible light, and dark matter shaped motions across the entire region. At last, even that halo began to blend into the shared landscape of the local group. We have crossed every useful border without passing through a wall. What remains is to gather these boundaries into one answer. At the edge of the Milky Way, we do not find a final star standing alone beside emptiness. We find a gradual change in density, motion, and relationship, until the question is no longer where the galaxy stops, but how softly one cosmic structure becomes part of another. The edge of the Milky Way is not a place where the galaxy suddenly stops. It is a long fading a sequence of regions in which one familiar sign after another becomes difficult to find. The crowded stellar disk thins first. Spiral arms lose their clarity. Cold gas becomes patchy, and the birth of new stars grows rare. Beyond that quieter disk, ancient halo stars continue on wide and tilted orbits. Globular clusters travel through the darkness like compact records of the early galaxy. Stellar streams preserve the remains of smaller systems pulled apart over billions of years, while dwarf galaxies still survive as separate companions inside the Milky Way's wider gravitational family. Farther out, even these visible traces become scarce, yet warm gas, hot plasma, and dark matter continue to surround them. The galaxy does not finish with one final object. It becomes less visible, less dense, and less easily separated from everything around it. What we know most directly comes from light and motion. Astronomers observe stars far beyond the bright disk map globular clusters and satellite galaxies, and detect long streams whose shared velocities reveal common histories. Radio telescopes trace hydrogen beyond much of the visible starlight. Ultraviolet and X-ray observations reveal portions of the thin gaseous environment surrounding the galaxy. Precise measurements of stellar positions show that the outer disk is warped and flared rather than neatly flat. The motions of halo stars, clusters, streams, and dwarf galaxies also demonstrate that the Milky Way contains far more gravitational mass than its visible stars and gas can explain. These observations do not show us a single outer wall. They show overlapping structures, each declining in its own way. The evidence is scattered across different wavelengths and different kinds of objects, but together it produces one consistent picture. The Milky Way is much larger than the luminous spiral we normally imagine. What the evidence strongly suggests is that our galaxy is surrounded by an enormous dark matter halo, assembled through a long history of mergers and growth. That halo probably contains smaller concentrations of dark matter, some accompanied by visible dwarf galaxies and others perhaps carrying few or no stars. The stellar halo appears to contain debris from many smaller systems absorbed by the Milky Way over cosmic time. The circumgalactic gas seems to participate in a slow circulation, receiving matter from satellite galaxies and stellar outflows, while also providing material that may eventually return toward the disk. The Large Magellanic Cloud is disturbing this outer environment, as it moves through it, creating wakes and altering the paths of distant objects. These interpretations are supported by observations and simulations, but their details continue to be refined. The outer galaxy is not a finished structure frozen in darkness. It is still responding to its surroundings. What remains unknown is where any one final boundary should be placed. Astronomers do not yet know the Milky Way's total mass with perfect precision. The exact shape and orientation of its dark matter halo remain uncertain, as does the full amount and distribution of gas surrounding the galaxy. Some distant dwarf galaxies may be securely bound to the Milky Way, while the histories of others are less clear. The number of extremely faint satellites is probably incomplete, because much of the sky is difficult to search deeply, especially through the crowded disk. Even the dark matter itself remains unidentified at the particle level. We can measure its gravitational effects without knowing what substance produces them, and where the Milky Way's halo begins to overlap with the local group definitions become dependent on the question being asked. A model can draw a useful radius. The universe does not place a fence there, so what would you find if you could travel to the edge of the Milky Way? You would first find that the journey had no agreed final destination. You might pass the last major regions of star formation and still remain among old disk stars. You might leave the visible disk and continue through a halo containing globular clusters and the debris of vanished galaxies. You might pass surviving dwarf companions and clouds of gas moving through an atmosphere too thin to see. Eventually, nearly every source of light associated with the Milky Way would lie behind you, compressed into a distant glowing structure. Yet the path of your spacecraft would still be shaped by the galaxy's mass. There would be no sudden release, only a weakening influence shared increasingly with Andromeda's smaller galaxies and the local group as a whole. The edge would be measured not by a wall before you, but by how the motion around you slowly changed. Perhaps the simplest image is the one we began with, a city seen at night from far away. Its dense centre shines brightly. Streets extend outward into quieter districts. The buildings become scattered, then the streetlights disappear. But roads continue beyond the lights. Travellers still move toward and away from the city. Its water communications and influence extend into places that no longer look urban at all. Eventually, even those connections weaken and become part of a wider region shared with other towns. The Milky Way is not a city, of course, and its stars do not follow roads, but its edge behaves in much the same gradual way. The luminous disk is only the brightest centre of a structure whose history, gas companions and gravity extend far into the dark, and now from that distant frontier we can turn back toward home. The dark matter remains invisible. The thin gas produces no horizon. The scattered halo stars are too faint to form a bright sky. But far behind them the Milky Way gathers into a soft wheel of light, holding the sun somewhere inside one quiet region of its disk. From Earth we see only a portion of that wheel as a pale band above the horizon, mixed with dust distance and the glow of countless unresolved stars. The galaxy appears close enough to cross the night, yet its true boundaries extend far beyond anything our eyes can show us. Its edge is not an ending. It is a place where certainty fades gently, where one structure becomes another, and where the universe remains connected without needing a visible line between its parts. You're still here in the same room beneath that turning galaxy. Nothing requires you to follow every distant orbit or remember every layer we crossed. The Milky Way will continue bending, gathering, shedding, and carrying its ancient stars through the dark. Its farthest influence will remain difficult to define, and that uncertainty is not a failure of science. It is an honest description of a galaxy whose borders are made from motion rather than walls. Outside your window, the night may seem still. Above it, our galaxy fades outward through stars, streams, gas companions, and unseen gravity growing quieter at every step until it gently becomes part of something larger. And for tonight that is far enough to travel.